Okay, first work is this RBC, red blood cell classification with machine learning. Uh, why this RBC classification is important? Because it's helpful to find disease in the body. It's helpful for drug studies and its effects on RBC. Also, this is helpful for hematological researches and similar studies. So in this work, I'm showing you some handcrafted features which are used for this red blood cell study and classification. And in this case, we are classifying four type of red blood cells. Then I use some feature selection for this complexity reduction of this model, which is utilized by forward feature selection. And next is a pattern recognition neural network is used to classify four types of red blood cell, and then the validation is by tenfold cross validation is performed, and also a SVM classifier is utilized to classify spherocyte and non-spherocyte. So let me explain you what classes we have. We have this, in this case, we have a stomatocyte, we have a biconcave, we have a flat disc, and we have spheroechinocyte. So the if Cephiro and echinocyte, they are type of red blood cell. When the red blood cell gets older, they become spheroechinocyte. In this case, if you have a red blood cell in the bank and they are suffering from spheroechinocyte lesion, then it's dangerous to transfuse this blood to a person. That's why we are addressing this stream classifier for the Cephiro and non-spherocyte cell classification. Okay, let's have a look at here. So A shows us a typical biconcave sample or normal red blood cell. Actually, the red blood cell will convert its morphology from one shape to another shape constantly because they are moving from the small capillaries and they change the shape. So these are normal red blood cell shape, but spherocyte and echinocyte, if they are plenty of them in the sample, this is a bad sign. Same thing happens to the stomatocyte, but in the normal blood, we observe them. We observe a few of them in normal blood. So A shows us a biconcave, a typical biconcave or a donut-shaped red blood cell. B shows us a flat disc. C shows us a stomatocyte red blood cell, and D shows us a spherocyte red blood cell. Okay, so there are these red points and blue points on the ring of the red blood cell. So what happens in this case is that I introduce these points to, actually there are new features in this study. I introduce these points to this classifier because this one can help us to classify red blood cells. As you can observe on this image, especially on the C, you see that there are plenty the points on the ring side, or the distribution is in a form that there are points on the highest place of this ring, and there are points on the lowest part of the ring, which they can be used to classify this red blood cell comparing to the other red blood cells. And also another feature is this one which we use here. This one we compare, we divide this thickness on the ring divide by thickness on the center of red blood cell. To be able to calculate this ring and the center, we project the red blood cell on the two-dimensional space, so this becomes a circular object. And then by binarization and using a mask, we convert them to a binary mask, which is background is black, and the area of the cell becomes white, and then we find a circle which can cover this red blood cell, and we find the center, or we find this DR, which is this thickness on the ring. So here are some example of training set. We on the upper side we have this this flat disc, and then B is stomatocyte, C is biconcave, and D is spherochenocyte, red blood cell. Okay, let's go next slide. So after this providing the sample, then we measure these values, these features for all these samples. So we have average thickness, we have volume, we have the surface area of the top view of the red blood cell, we have the top view surface area divided by volume, we have total surface area. These are the parameters I used in this work, and these are the values for all these samples and all these groups. Okay, so let's look at some result in this work. Because we had 13 features in this work, I showed you a few of them in the previous page. We had 13 features. What we used is that we employed a sequential forward feature selection algorithm. This method adds features from a candidate subset while it's evaluating the classification error. So it constantly adds these features to the feature set and then classify them, then provides us some result. What happens here when we add a feature and then this feature drops the classification accuracy, then it's not a good feature. And if it increases this one, it increases the classification error, then it's a good feature. So after this forward feature selection, it turned out these 5 features are the best. So one is average thickness, one is sphericity coefficient, one is upper side of the ring divided by the lower side of the ring, surface area to volume ratio, and then parameter of the projected surface area. On the right side, we can see the distribution of these parameters for all these classes. And on the left side, we compare these 2-dimensional features versus 3-dimensional features. By 2-dimensional features, we mean if we use just a normal intensity microscope, how much error we can have. And then with 3-dimensional features, we are comparing this one with digital holographic microscopy, which can provide us 3-dimensional features of this red blood cell. Okay, let's look at some results here. Here, after this training of the model, we gather some sample from different patients, and we image them with red blood cell with DHM, and then now we are trying to classify them and see which morphology is dominant in the sample. On the left side, we see on A, we see a sample which suffers from the stomatocyte. This is kind of disease which some people suffer from. And the B is a normal red blood cell. C is a spherocyte. This one is a echinocyte, and this one has a lot of flat discs. So on A, when we look at this one says there is 0% of flat disc. There is 76% of the stomatocyte, 10%, 11% of biconcave, and 10% of these echinospherocyte. On B, we see a flat disc, 7%. We see stomatocyte, 18%. We see biconcave, 74%, and echinocyte, 0. On the C, we see flat disc, 0, stomatocyte, 12%, biconcave, 10%, and echinospherocyte, 77%. D also shows us that these echinospherocyte are dominant, and on E, we see that these flat disc are composing most of these cells in here.